In the previous lecture, we've looked at some concepts and definitions that we'll use during the course of our study of thermodynamics. In this lecture, we'll continue our discussion on some concepts and definitions, and we'll look at the definition of the state of a system, in particular, the equilibrium state. Then we'll look at process and a path. There are different types of processes that a system may undergo. Now, to begin with, let's look at what do we mean by state of system or the substance that is in that system. Now, the working substance that is present in the system or that may be flowing in and out of an engineering system may exist in various states. Now, the state of the substance is described by the macroscopic properties. We've seen in the previous lecture that these macroscopic properties could be of intensive or extensive. Now, the state of a working substance within the system can be described by these set of properties. For example, pressure, temperature, density, specific volume. Now, often the state of the substance is referred to as the state of the system. But we in thermodynamics want to work with what we call as equilibrium states. So the properties of a substance in a system can vary in space and time. And that means if you have a gas, then you need to define the pressure of the gas at different locations within the gas, and that pressure may change with time. So the properties of a substance can change spatially and temporally. But the macroscopic systems that we are going to deal with, all macroscopic systems exhibit some kind of a memory. Of their recent history, and this memory fades with time. For example, if you stir a cup of tea, then it continues to swirl. That means at a given state it knows what happened in the previous state, but later the motion damps down, and if you wait sufficiently long, then that memory fades away. So it won't matter how you arrived at that particular state. But to look at more relevant example, let's look at a system where we have gas in piston cylinder arrangement. So we have a cylinder that has adiabatic walls. Recall that adiabatic walls are those which do not allow heat transfer. The cylinder is provided with a movable piston, which again does not allow heat to transfer. And here the cylinder is filled with a gas. Now, for this discussion, we can consider that the piston is massless. We have two masses kept on this piston, denoted by M1 and M2. So if you wait sufficiently long, then this gas would be in a steady state where there would be no gradient pressure. That means the pressure at any of this location would be fixed, and other quantities and other properties would also be fixed. Now, what we do is that if we suddenly remove this mass M2, what will happen is that the mass that is kept on the piston will go down, and the pressure, the gas, would be higher than the net force that is being applied on piston. Therefore, the piston would move to another location. So while this sudden process of expansion of the gas is taking place, the properties within the gas would vary in space and time. But later on, if you wait for sufficiently long time, the transients will die down, and then we have a new state where the gas again will have a new pressure, which obviously would be lower and will have a higher volume, and the piston location somewhere above original location, and we'll attain a new state. So any kind of system, including the system that we've seen over here, the piston cylinder arrangement with a gas, any system will have a tendency to evolve toward a state in which the properties of the substance that is contained over here, this example gas, would be determined only by intrinsic factors and not by previously applied external. That means we had a gas which was in a state which was not evolving with time. Then when we suddenly removed the mass, gas expanded to some transients where the pressure would be different within the gas at different locations, but eventually the piston settles down to specific location above the original piston, and the gradients pressure and all other quantities within the gas settle down, and it reaches a state where it forgets what was the history and how it came to that particular state. In such kind of states where the system loses its memory as to how it has attained that state is called the equilibrium state, and obviously such equilibrium states are steady state or time independent. In other words, we say that equilibrium states are those where the system can be described by a small number of variables. For example, if we had to describe the state of the system over here, the state of the gas while it was expanding, then we would have to define the pressure at various locations. But once it has attained this equilibrium state, then all that we need to define is, in this particular case, is the pressure of the gas is constant everywhere and its total volume. Alternatively, if you have the mass of the gas is fixed in this closed system, therefore you can describe the state of the system using pressure and its specific volume. Equilibrium state of the system is defined by the properties of the substance that is contained in that system. For a given equilibrium state, you have unique set of properties. But to define the equilibrium state uniquely, it is not necessary to specify all the properties of the substance. And that is very important to note. So it is not necessary to specify all the properties. That means the properties of a substance are not independent. So there are only few properties that are needed to uniquely define the state of the system. Or in other words, there are only few properties that are independent. And when we talk of properties, we always talk of the properties of the substance in the equilibrium state. Now, if these independent properties are fixed, then we uniquely can identify the state of the system, and from these independent properties we can define, or we can get all other properties of the system. How many properties do we need to define the state of the system? That means how many properties we can independently choose to define the state of the system. So we'll look into that in detail later, but as of now it is important to note that for a homogeneous, so homogeneous means that it has only a single phase. So if we have a homogeneous system that is having a single phase of a pure substance of known mass, then all we need is two intensive properties to uniquely define the equilibrium state. For example, in this case, let's say if this gas was a pure substance, say helium gas, then we can define the state of this system using pressure and the total volume. But for a fixed mass, then we can define the state of this system using pressure and the specific volume. That is, these are the two intensive properties with which we define the state of the system. Later on, we'll see that what happens if we have a pure substance with different phases, or a multi-component system with in different phases, then how many properties uniquely identify the state of the system. That we'll look at later when we discuss the properties of the substances in more detail. Now, note that if you have an isolated system that does not allow transfer of mass with its surroundings or energy, that means it's completely isolated from the surroundings, and if you wait sufficiently long, an isolated system will always attain thermodynamic equilibrium. So the equilibrium that we are interested in is thermodynamic equilibrium. And what do we mean by this thermodynamic equilibrium is that we'll have all types of equilibrium. That means there is equilibrium for all different types of phenomena that might occur. For example, there could be equilibrium. So you can have mechanical equilibrium, you can have chemical equilibrium, you can have thermal. So what do we mean by mechanical equilibrium? So mechanical equilibrium is attained when there is no unbalanced force in the system. And there is no unbalanced force not only within the system but also between the system and the surrounding. When you remove this mass m2, then the force that the gas exerts on the piston in the upward direction, that is the pressure times the cross-sectional area, is larger than the force that is being applied by this mass and the effect of atmospheric pressure on this piston in the downward direction. And there is an imbalance the force. But when this piston settles down to a final equilibrium state, then all the forces are balanced. That means there is neither any pressure difference between the gas, and also there is no pressure imbalance or force imbalance between the system and the surroundings, and that is what we call as mechanical equilibrium. Similarly, equilibrium can also be of chemical nature. That means by chemical equilibrium, we mean that there is no change in chemical composition of the system due to any reaction or mass transfer to the system. For example, you've seen in your high school where you studied acid-base dissociation reactions, you have seen that, let's say you have this acetic acid, then can dissociate acetate ion and hydronium ion. But this reaction can go in either way, and if you wait, then this reaction will attain an equilibrium where you will have no change in the species that are present at any given time. That is, the concentration of all the species do not change, and that state is said to be chemical equilibrium. Similarly, is something called thermal equilibrium. So thermal equilibrium is that when you have a system, let's say with diathermal walls. Recall that diathermal walls are one which allow the system to exchange heat with the surroundings. Now, if you have diathermal wall and there's no heat transfer with the surroundings, then we say that the system is in thermal equilibrium with its surroundings. Now, when a system is in mechanical, chemical, and thermal equilibrium and any other type of equilibrium, when all these conditions are satisfied, then we say that the system is in thermodynamic equilibrium. So whenever we talk of equilibrium state, what we mean is that the system is in thermodynamic equilibrium. If any of these conditions or any of this mechanical, chemical or thermal equilibrium, the conditions for these equilibrium are not satisfied, then we say that the system is in a non-equilibrium. And again, recall that the properties of the substance corresponding to an equilibrium state are the same. That means we look at this example over here. So here the system and the equilibrium state is described by its pressure and the volume. Now, if we arrive at this equilibrium state by any other way, for example, you can pull this piston again up and then it will come down because it has this mass on itself, then it will attain that same state which you could have attained by any other process. But the properties of the substance, which in this case is the gas, corresponding to this particular equilibrium state, will always be same irrespective of the way the state has been attained. In other words, at thermodynamic equilibrium, the system loses its memory and it is uniquely defined by the properties. And these are only few properties that are needed, which can be independently varied, and these are the properties that you need to define the state of the system, and all other properties will depend upon these. So for a pure substance, with a homogeneous system of a pure substance, all we need is just two properties to define that state uniquely. Now, note that virtually no system of physical interest is in thermodynamic equilibrium. However, slowly evolving systems with small spatial variations can be said to be in quasi-equilibrium. So, quasi-equilibrium means that the system is evolving slow enough that you can assume the system to be in equilibrium. That means the variation in the properties can be considered to be negligible, and still you can define the state of the system using only few properties such as pressure and volume for the gas that is contained in a cylinder piston arrangement. However, if that gas expands rapidly, as it would do when you remove the mass on the piston, then that gas will not be in this quasi-equilibrium, it will be in non-equilibrium state. So analysis of systems in non-equilibrium states require the complex study of non-equilibrium thermodynamics. And this is actually beyond the scope of this course. So what we are going to study in this course are systems which are in equilibrium or quasi-equilibrium state. And this is called equilibrium thermodynamics. So throughout our course, we are only going to look at equilibrium or quasi-equilibrium states of the system. Now let's look at the concepts of process and path. For this, we can go back again to the same example of the gas contained in piston supported by a cylinder. So here, let's say that the gas is in an equilibrium state initially. Let's call that state as A. And we know that now we can define the state of this gas with pressure volume. And this gas then expands upon removal of this mass, then goes to another state, which is defined, let's call it as B, described by pressure, volume, Vb. Now, there are many ways by which you can go from this state to another state. So whenever the system evolves from one equilibrium state to another equilibrium state, we say that it has undergone a process. But sometimes what happens is that in certain types of processes, that when the system evolves from one state to the other, it goes through a series of equilibrium states. So if you have, let's say, state A that is in equilibrium, and you go to state that is a different equilibrium state of the system, but if you do it in a way that the system goes from the first state, the initial state, the final state, through series of equilibrium states or quasi equilibrium states, then we say that this series of states, the initial, the final states, and the series of equilibrium states are called as a path. For example, let's go back to that same example where we have this gas in the cylinder and we have this piston on which two masses are kept. So initially, let's say if we plot the state of this on a P versus V diagram, and the fact that we can plot this because we can define the equilibrium state of the system using two properties, that is pressure and volume. So the fact that I can plot this point on this PV diagram is because we can describe the state of the system using only two variables. That is, it has attained a very simple state that only two variables, which are very small number of variables, are sufficient to describe the state of the system. So that is a property of a pure substance which has a single phase, and that's why we can describe it, that state, with only two variables. So let's say the gas is in state A described by this pressure PA and volume VA. Then when we remove this mass, then the gas, and it will attain a state where it will have higher volume, no doubt, and lower pressure. And again, I am able to plot this state because I have equilibrium state denoted by, initial state is denoted by A. But can I plot the intermediate states on this diagram? No. Why? Because when I remove this mass, second mass, from this piston, then the gas expands violently, and at any of these intermediate states, the state of the gas cannot be described by only two variables, that is pressure or volume, because the pressure might vary within the gas. So I cannot plot that kind of a process on this PV diagram. But for representation purpose, we'll typically plot it by a dashed or dotted line. That doesn't mean that the gas goes through this pressure and volume. In fact, this dashed line has no meaning, just it has, the only meaning is that just to show that the gas goes from state A to state B. Other than that, it has no meaning at all. However, if we do another type of experiment, and in this case, what we do is that we have again the gas same state, that is at pressure PA, PB. And recall that this example, the gas to be enclosed, the cylinder and piston that are insulated. So initially the gas is have this state A over here, and we have one mass, let's say m1. But instead of the second mass, what I'll do is, let's say we'll replace this m2 mass with an equivalent mass of, let's say, fine sand particles. Now we can go from state A to state B to another process. This time we have sand instead of this mass m2. So what we do now is, let's say we remove the sand particles one by one, or with very small pinch we remove the sand particles every time. So what you will see is that because we are just making a small change to the system, then the gas will stand very slowly. So we can assume the process going through quasi-equilibrium states. So through a series of quasi-equilibrium or equilibrium states, we expand the gas and take it from state A to the same state B, where we have removed this mass m2 completely. But this time the process is not violent. We are able to go through states which are in equilibrium every time. And let's say we now say that we go from state A to intermediate state. Because we are going through a sequence of quasi-equilibrium states, for each of that state we define that, or we can plot it on a pressure versus volume plot, because for equilibrium or quasi-equilibrium states we can represent those states only with these two variables for this particular system. So let's say you go from state A to state, and because we are going through a series of equilibrium states, we can plot all these states, and that's why it is can be plotted using a solid line. So whenever you see a solid line, what we mean is that the system is going through a sequence of equilibrium states. And this is not the only way you can go from state A to B. You can go through many different states as well. But for this particular example, for one particular way, you will go through one particular process which is denoted by a solid line. Note that because we are going through a sequence or series of equilibrium states, this solid line is the path. But this is not the path, because the dotted line is not the path, because you are not going through a series of equilibrium states. Now note that in this process where we are taking pinch of sand away every time, and then we are slowly evolving the A to, we can also do the same process, the opposite process, by adding a pinch of sand every time. And if we do so, we'll again follow this particular path. That means this process that is denoted by, or that is depicted by this continuous line, is the reversible process. So that's another definition that you need to know. So any process that passes through a series of equilibrium states is also a reversible process, because a reverse process can go through the same equilibrium states if we just reverse the way in which we are taking the system from one state to the other. On the other hand, if we remove the mass m2 on the piston suddenly and the gas expands violently before it settles down to the equilibrium state B, then that process that is shown in this dotted line over here cannot be reversible. In fact, that is irreversible process. So irreversible process is one that does not go through equilibrium state. That means it goes through a series of non-equilibrium states, and such a process is an irreversible. We denote such processes diagrams like P diagram on using a dotted line. Lastly, we need to define something called cycle. So cycle is that, let's say you start from state A and you go to state B. then you go back from a different path from state B to state A. So the point is that if you start the initial state and the final state of the system, those states are the same, then we say that the process is a cycle. That means the series of processes in which the initial and final state is same, that series of processes is called cycle. So if you go from path 1 and go back by path 2, so we'll say that this series of processes or path 1 and 2 constitutes a cycle. So we've already seen examples of few cyclic processes. For example, we've seen a steam power plant. There, if you consider an element or a parcel of water, then it passes through various components such as boiler, then turbine, condenser, the pumps, and it goes through various components but comes back to the same state which it started with. So that parcel of water undergoes a cyclic process. Similarly, in a refrigerator, an element or parcel of the refrigerant flows through different components and it also undergoes a cyclic. So here we've shown an example of cyclic process where you start from the state A, that is equilibrium state A, then you go to different states and then you come back to the original states. So with this, we have finished all our discussion on the definitions and the concepts that you need to do thermodynamics. Now, in later lectures, start looking at the various laws of thermodynamics.